As we move into section 4.4, we're going to move from homogeneous differential equations to differential equations where we have a particular value on the right side. So we have it in the same form where we have our second derivative, our first derivative, our y on the left, but instead of being equal to 0, then this time we're equal to some function. We could call that f of t. So when we looked at the previous section, when we were equal to 0, we realized that in order for our second derivative, our first derivative, and our function to combine as a linear combination and equal 0, that we were limited to what our solution could look like. So typically our solution was of the form e to the rt with the coefficient in front, because when we took the derivative and the second derivative of that function, then we ended up with something of the same form. And then when we added and subtracted linear combinations of that, they were able to cancel out and give us a 0. And then we went on to see that when our solutions to our characteristic equation were complex, then we introduced solutions that involved cosine and sine as well. Well, in this section, we're going to look at situations where we're not equal to 0 to where we're equal to other things. And what we're going to do is we're going to start out with a basic assumption of a particular format of our solution with undetermined coefficients. Now, before we go on in and actually solve some, let's talk about what type of functions we can have on the right and use this method of undetermined coefficients. So if our right side, we'll call that f of t, if that's a polynomial, then we can use the method of undetermined coefficients for that. If our right side is something where we have e to some power of t, then we can use the method of undetermined coefficients for that. Also, if we have cosine or sine, that's going to be a method of undetermined coefficients problem. And then if we have a combination of these, if we have, for example, a t squared e to the 3t, where we have something that has a polynomial piece to it times something with an exponential, or something with a polynomial times a trig component, then we can use method of undetermined coefficients to find out how many of these pieces we would need, so that when we take their first derivative, second derivative, and add some linear combination of them together, we get our function on the right side. So one thing that we have to keep in mind is that our solution can't also be a solution to the corresponding homogeneous equation. What do I mean by that? If we come up with something that we think is the solution, but once we take the first derivative and second derivative, if we look at this particular example, if we have something and we take, uh-oh, my screen's running away from me. If I take the second derivative of this and the first derivative of this, if I add them together in the way described above, which is the second derivative plus 4 times the first derivative minus 5 times the function, if the function that I pick to be y turns out to, when I take the second derivative, first derivative, and I combine them linearly, if that gives me 0, then that means y is the solution to the homogeneous equation. It's the solution to the homogeneous. So if it's a solution to the homogeneous, then 0 can't equal something else. So we have to be careful in those situations, and we'll look at some examples of that. So let's look at, well, what does the format need to be when we have various situations? Let's get a new screen. So let's suppose we have y double prime plus 3y prime minus 7 equals t squared, or let's say 3t squared. Then we're not just going to let y be a t squared. We're going to assume that when we take the derivative of this, that our solution may contain not only second degree, the second degree term, but also every possible term down to t to the 0. So we could have bt, or we could have a term without a t in it. What if we had y double prime plus y prime minus 3y equals t cubed e to the 4t. Then for the polynomial part, our solutions could be anywhere from t cubed to t squared to t to the first to a constant times e to the 4t. Now, occasionally, we're going to run into situations where if we list these particular pieces, then what we come up with would actually be a solution to the homogeneous. So this is slightly related to what we talked about in the previous section when we had double solutions, double roots, and we said that in order to get two solutions and for them to be linearly independent, then we had to pick up an extra t to go with it. So let's see if we can find an example like that. So let's take a look at this particular example. If we looked at the corresponding homogeneous equation, which would be y double prime minus 4y prime plus 3y equals 0, notice that our characteristic equation is r squared minus 4r plus 3 equals 0, which factors to r minus 3 times r minus 1. So we get r equals 3 and r equals 1 as solutions to that. So notice that one of our solutions to that is c1 e to the 3t, which is what we have on the right side. So e to the 3t, that would actually be a solution to the homogeneous equation. So for our particular solution, and we call this a particular solution when we have a particular value on the right side here instead of just 0. So for our particular solution, it can't be just simply in the form of e to the 3t. But for it to be related to that, but linearly independent, then we can pick up a t just like we did in the previous section. Notice that still makes e to the 3t part of our solution, but this one is not a solution to the homogeneous. So anytime that this function is also a solution to the homogeneous, then we need to increase our coefficient by a power of t. If it's a single solution, we increase it by a power of t to the first. If we have a double solution, we're going to increase it by a power of t to the second. So let's look at an example of that. If we have one like y double prime plus 4y prime plus 4 equals e to the negative 2t, notice that r squared plus 4r plus 4 equals 0 would be the characteristic equation to our homogeneous. So if we factor that, we would get r plus 2, r plus 2. So we get r equals negative 2 twice, which means for the homogeneous, our solutions would be C1 e to the negative 2t, and our other solution would be, we would have to pick up a t so that we are linearly independent to go with our e to the negative 2t, which means that for our particular solution, it can't just be e to the negative 2t or t e to the negative 2t, because each of those are solutions to the homogeneous, which means that when we take the first derivative of this and the second derivative of this and plug those into our function, and this is supposed to be a y here, that when we do that and add those together, that's going to equal 0, not e to the negative 2t. And of course, those things are not the same. So if both of these, when they are in our solution, make it equal 0, then how are we going to get e to the negative 2t when we add our derivative 4 times our first derivative plus 4 times our function? So to be in the form e to the negative 2t, but to not be part of the homogeneous solution, then we pick up another t. So e to the negative 2t and t e to the negative 2t are both homogeneous solutions, so we pick up a second t squared out front. And then we can find some coefficient to go with that, such that this would be a solution to our particular. So let's work through one like this and see how this is going to work. Let me show you real quickly in the book. Here's how the summary of this method goes. That if we have a polynomial, it could be multiplied by e to the rt, that we're going to list t to that power, and then every power down to a constant. Instead of using a, b, and c, they're just using different subscripts of a. But to keep from confusing those, I would advise a, b, c, d until we get down to a constant. If there's not an e to the rt, then there's no e to the rt here, but we could have an e to the rt there. So this is going to be the form of our solution. And then if for our auxiliary or characteristic equation, if this r is not a solution, then we don't pick up an extra t to go with it. We don't increase the degree of our polynomial. In the previous example that we looked at here, our polynomial was of degree 0 because we just had a constant out front and understood 1. So that's like having t to the 0 out front. So since our solution, our r, was a double root, then that told us how many t's we had to pick up out front. We were at t to the 0 out front to begin with, but since we had a double root, we had to pick up 2 t's, or t squared, in front of our particular solution. If we look at the one before that, I think it's this one, if I can. Yeah. So when we looked at this, our first thought would be that our format would be of the form a e to the 3t. But then when we look at our auxiliary equation, r squared minus 4r plus 3, we notice that 3 is one of those solutions. It's not a double solution, but it's one of those solutions. So it can't just be e to the 3t. So since 3 is one solution, then we have to pick up a t to be part of our particular solution. I'll go back. So if r is not part of the auxiliary or the characteristic equation, we don't pick up any t's out front. If it's a single solution, like the previous one, we pick up one extra t out front, so our degree goes up by 1. If it's a double root, then our degree of t goes up twice. And then we have to include each power down to 0. The same thing applies if instead of having e to the RT, if we have either a cosine or a sine on our function on the end. So let's just work through one. So let's take a look at this one. So just looking at it, we would suppose that our equation should be of the format. I'm going to have to zoom out just one moment. So let's take a look at this one. So at first glance, it appears that our solution should have an e to the 5t, and out front, since this is t to the first, we should have an a times t and then a b. Since that's t to the first, we need a t to the first term and a constant term. But we need to look at our characteristic equation to see what the solutions to the homogeneous look like. So we have an r squared minus 10r plus 25, and for the homogeneous, that would be equal to 0, not equal to this. So if we factor that, we get r minus 5 times r minus 5. So we get r equals 5 as a double root. That's the solution twice for that. So that means for our homogeneous equation, we would have something of the form C1 e to the 5t and C2 t e to the 5t. So since 5 is a double root of this, then we're going to have to pick up not just one t, but two t's in front of this. So that's going to make our particular solution of the form a t cubed plus b t squared e to the 5t. We go back and look at our list. We don't have to go all the way down to 0 after we multiply times the t's out front, but on the inside we do go all the way down to no t's. So notice on the inside of the parentheses we have a t to the first and then no t, but then we pick up t squared on the outside. When we distribute that, we don't have to go down to 0 on the inside. So this is going to be the format of our particular solution. So by means of undetermined coefficients, our undetermined coefficients that we're looking for are a and b. We need to find out what do a and b need to be such that when we take the second derivative of this, the first derivative of this, and our function and add them together, we get the right side. And you may have noticed that all the other ones we did were in terms of y. Here, the one I picked was x, so this should be x instead of y. So if our generic equation is this, we need to get our first derivative. So notice we have a product where this is u and this is v. So u prime would be 3a t squared plus 2b t. So that's u prime times v plus u times v prime. So that's our first derivative. And then our second derivative is the derivative of this. So we could probably would be best to simplify the first derivative. So both of those have an e to the 5t. So let's factor out e to the 5t. And that's going to give us 3a t squared plus 2b t And then when we distribute 5 to this, that's going to give us 5a t cubed plus 5b t squared. And then we could simplify that if we wanted to. We could combine our t squareds and our t squareds there, or we can just leave them as they are for now. So then our second derivative, if this is u this time, then u prime would be 5e to the 5t times the parentheses. So that's u prime v, and then plus u times v prime. So v prime would be 6a t to the 1 less power, 2b, the derivative of t is 1, 15a t to the 1 less power, plus 10b t to the 1 less power. So u prime v. So that's our second derivative. So when we linearly combine our second derivative, which is all of this, minus 10 times our first derivative, so minus 10 times this. So this was our first derivative, so we're going to take that times negative 10, and then we're going to subtract or add 25 times our original function, this. So this one is one of the messier ones, but let's see if we can, if I can zoom out and then write all of this. So our second derivative, 5e to the 5t, in fact, let's do this. Let's factor e to the 5t out. So for our second derivative, if we take e to the 5t out front, for the first parenthesis, we're going to have 5 times that first parenthesis. So 5 times 3, so 15a t squared, 10bt, 5 times 5, so 25a t cubed, 5 times 5, so 25b t squared. And then we're going to add that with this parenthesis. We've taken the e to the 5t out front, so then we have 6a t plus 2b plus 15a t squared plus 10bt. So this e to the 5t went out in front of all of that. So then we have that minus 10 times, so let's go ahead and distribute 10 times our first derivative, and it's a negative 10, so let's do negative 10 times the first one. So negative 10 times 3, that's going to make that negative 30 a t squared. Negative 10 times that, so negative 20 bt. Negative 10 times that, so negative 50 a t cubed. Negative 10 times this, so minus 50 bt squared. And if I take this parenthesis off, then we've just gone ahead and factored e to the 5t out in front of that as well, because the first derivative has an e to the 5t in it. So I'm just going to let that be the common factor that goes out in front of all of that. So then we do plus 25 times our generic. So let's take the e to the 5t here, and then we're going to have 25a t cubed plus 25bt squared. That e to the 5t, we didn't write it because it got factored out all the way to the beginning. So when we add all that together, that should equal 2t e to the 5t. So that's a huge mess. But we have a lot of things in common. So let's notice that we have an e to the 5t here. We have an e to the 5t there. Our coefficient of t is 2. And then we have no t squareds, no t cubes, and no constants. If we think about e to the 5t being pulled out to the front, here it's on the right side, but on the left side it's to the front. So for our t cubes, on the left we have, let's go through and highlight all of our t cube terms. So we have a t cube term here, and then we have a t cube term here. We have a t cubed term here. So we have 25a t cubed, another 25a t cubed, and then minus 50a t cubed. So 25 is 50 minus 50. So all those cancel out. So there are no at cubed terms on the left. Now let's look at the t squared terms. We have a t squared term here, 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 and here. So we have 15, 40, 55. Oh, we have to be careful because some are A's and some are B's. So let's do this. So we didn't have any t cubes. So for the t squares, I'm going to do a square around the A's. So if they're the at squares, notice these just canceled. Here's 15at squared, another 15a, so that's 30at squared minus 30at squared. So those cancel. So we have a 25bt squared here, a 25bt squared here. That's 50 minus 50bt squared, so those cancel. So then let's go down to our t terms. So here's a t term, here's a t, here's a t, here's a t. So for the bt's, here's 10bt plus 10bt, that's 20bt minus 20bt, so those cancel. So that leaves us with, oops, not t squared. For our t, we're left with a 6a. That tells us how many t's to the first we have on the left. Now, if you look on the right, we have 2 t's to the first. So 6a is how many t's to the first we have on the left. 2 is how many t's to the first we have on the right. If we divide by 6, then we get a is 2 over 6, or 1/3. So what else do we have on the left? We have 2b, and I think that's it. Every other term has been accounted for. So 2b equals what? 2b is our constant on the left, and if we look on the right inside, once we factor the e to the 5t out, there is no t to the 0 term. So 0 t to the zeros. So if we divide both sides by 2, then of course b is 0. So for our particular solution, it turns out that, and there I go writing y again. This is supposed to be x. So for our particular solution, we have 1/3 is a. So we have 1/3 is a. That's t cubed. B is 0, so 0 t squareds. and that's times e to the 5 t. So our guess was that our solution was in this form, something t cubed plus something t squared. And it turned out that we didn't have any t squareds and that the amount of t cubes we need was 1/3. So that was our particular solution.